And we are live now. Yes.
I have a question about the writer. So
okay, so just to introduce anyone listening later online, we're taking questions about the final project to start with. Yes.
So you specify the font size for the write-up?
Yep.
Is that the same font size we're going to use for the write-up?
Yes. So there's only one write-up, and that is, it's not a report, it's a poster presentation. And so the large font size is a recommendation for readability, because if you use a 12-point font, it's not going to be readable as a poster presentation. So it's just a guideline. You're not graded on following the instructions on font size, but you are graded on the clarity of presentation and the readability of the poster presentation.
I guess my problem was that I was writing the introduction,
Mm-hmm.
and then you said that it should be only one page. So then I was trying to make it as short as I could, just to make it so that it would fit in one page, and also the font size specifications.
So you can spread your introduction onto 2 pages if you want to. You don't need too much of an introduction, although if you're using some data set that is unfamiliar to everyone else, then it might be best to have a somewhat longer introduction, and that's fine if it goes on to 2 pages. Yeah. All of that stuff about formatting, like it is guidelines. I think they're generally good guidelines, but like all guidelines, there are cases when they don't hold. There are examples of how to write a caption for a figure. Those are really good guidelines, I think, like writing a descriptive caption. And there's something that, even though that's not an item on the rubric, like, caption does this and this, it definitely contributes to my impression of the readability of the poster when I see a good figure caption. So yeah, you don't need to treat them as law, just as hopefully helpful guidelines. And there's also there is also, I believe, a link in there to some suggestions on doing descriptive statistics. If I could give some impressions from past semesters of doing this project, one of the most difficult things, I think, are common ways that people have gone wrong is in presenting their statistics, in providing an easily readable table of making output from their analyses that contains the information that the reader wants and not a whole lot of other things. That's probably the most challenging part, because by default, SPSS doesn't really do that. SPSS gives you everything in a small font. So if you take and do a screenshot of that onto your poster, you end up with this thing that is someone coming by and looking at your poster isn't going to want to read. But that would be my biggest suggestion, I guess, about presentation, is just trying to think about how to clearly and concisely present your results. I had one request about another data set, the Youth Behavior Risk Survey. Looks like a great data set. I posted it in CSV format on the project's webpage, just to make it a little bit easier. There were too many variables in it for me to recode all of them, but Tony and I will take requests for generating SPSS data sets as well. SPSS does import CSV files, but you'll find that some recoding of the variables might be required to turn them into categorical variables. Any other questions? All right, well, there will be more chances to ask questions. Make sure that you introduce yourself in one of the groups online. I'll check. I think that maybe the other projects group was almost full. If it gets over full, I'll just create another discussion forum for others. I didn't know how many people would take which option, so I just kind of guessed. But I'm glad to see a number of people analyzing their own data sets or other data sets from the city. All right, so let's get started. We're going to deal with the analysis of categorical data today, and there are whole courses on categorical data analysis, and we're just going to cover one class's worth. And we're going to cover the situation in which we have two categorical variables, and we're interested in whether there is an association between those variables. By the end of lecture and lab today, you should be able to perform Pearson chi-squared tests of independence on R by C tables. That means number of rows by number of columns, and of course also identify the assumptions behind that test and situations in which you would want to use that test. We're going to define and calculate relative risk and odds ratios for two binary variables, and name a few alternatives to the chi-squared test for other situations. This is sort of covered in your textbook in chapter 6.3, although the textbook is fairly brief on this stuff, and I didn't actually find in there a definition of relative risk and odds ratios in our textbooks, but you'll be getting lots of those two things between your biostat and epi courses as you go along, and we'll define them today. So this is as a motivating example, and this is kind of an old study, although there have been, I've noticed several new data sets like this have become available just in this fall. And if I had had a little more time, I would have updated this whole class to use one of these more recent data sets. But a lot of them their basic analyses are along the same idea as this data set and the associated study. I've also posted the published paper with under the lecture today, so you can take a look at it in more detail afterwards if you're interested. But it's an analysis of all court trials in Florida over about a 10-year period where there was a potential for the death penalty. So there are capital homicides where there was a conviction and a possibility for a prison sentence or a death penalty. And this was an analysis of what verdict was, what the sentencing was, and looking at whether there was an association with the race of the defendant. With the motivating question of, is there evidence of discrimination in the application of the death penalty? Looking at that probabilistically and how we're going to analyze the data set, what we're going to look at is the death penalty verdict statistically independent of the race of the defendant? As with all of our other hypothesis testing, we need a null and an alternative hypothesis. So, and as usual, the null hypothesis is the hypothesis of no difference. And in this case, that is going to be that the death penalty verdict and race of the defendant are independent, with the alternative hypothesis that they are not independent. Equivalently, and this would be
using notation that you've already used back when we were looking at the hypothesis tests for two independent samples, the null hypothesis would be that the two proportions are equal, and the alternative that the two proportions are not equal, where those proportions are the probability of the death penalty verdict for white defendants and for black defendants. So nothing new so far. This first statement is a somewhat different statement of null and alternative hypothesis than you've used before. You could take the proportions approach here and use methods that you have already learned in this class, where you'd make the normal approximation to the binomial distribution and perform a two-sample z-test. You could construct a confidence interval on the difference in the two proportions, and you already know how to do that. It's an interesting comparison to make for something like this, to compare these two different hypothesis tests. For large samples, they will come out to be to give you similar results. What we're learning today, this contingency table or frequency table approach, the idea behind it is very different though. It's not around the idea of proportions, it's around the idea of how many counts in each of the entries of this R by C table would you expect if those variables are independent. And we will calculate the number that you expect if they're independent, and then our statistic will be based on how different the observed counts are from what we expect under that assumption of independence. And this is a somewhat more general approach than the proportions approach, because with proportions, we're only dealing with binary variables. So in order to do this two-sample z-test on two proportions, that is only going to work for two binary variables. As soon as one of them has 3 levels, then you can't use that approach anymore. But you still can use the contingency table approach. So what do we mean by this number of expected counts? So these are how many entries in each cell you would expect if there is no relationship between death penalty verdict and race of the defendant. And in order to fill this in, you start by filling out the margins of the table, so that we have the total number of white defendants, 4,900, the total number of black defendants, 5,100, and then the number of death penalty verdicts, the total is 364, and the number of prison sentences is 9,700. So overall, the proportions of black and white defendants are pretty close to the same, but the proportion of defendants who did not receive the death penalty is much higher than those who did receive the death penalty. So if you were going to calculate this under the assumption of independence, do you remember about the probability of 2 independent events occurring? How you calculate that if they're independent? What's that? You multiply them, exactly. So all you have to do is, if we're going to fill in this column of a white defendant receiving the death penalty, all you have to do is take the probability of the defendant being white times the probability of receiving the death penalty, and that's all there is to it. So it's the probability of someone in this study being white is 364 out of the 10,000, and the probability, or sorry, is 4,900 over 10,000, and the probability of receiving the death penalty is 364 over 10,000. Simple enough, right? And if you calculate that, you'll get 177.5, I think. Yes?
Calculating probability of death penalty. Are you talking about,
Sorry?
when you talk about the probability of receiving the death penalty,
Yeah.
are you talking about the total including black and white, or just white?
So when I talk about probability of receiving the death penalty, I'm talking about everyone, just the overall probability of receiving the death penalty. Like in this right here, this probability of yes, this is everyone who received the death penalty, 364 divided by 10,068. So this, to get this 177.5, you go 364 over the total times 4,909 over the total. That'll give you a probability. Then you multiply by this total to get a count. Yes? Sorry? Yep, same thing could have been done for anyone or all of the cells in this table. That's right. It's just filling in these counts under the assumption that receiving the death penalty verdict and race are independent. But as it turns out, you don't need to calculate that for everyone. As soon as you calculate one of them in this table, you can fill in the rest just by subtracting. And I'll give you an example here. You don't need to do all that multiplying to fill in this next row here. All you have to do is do 4,909 minus 177.5. Right, and this one has to be 364 minus 177.5. That is the expected number of black defendants receiving the death penalty. And then once you've calculated either one of those, you could fill in the last cell just by subtraction as well. And this, by the way, is the number of degrees of freedom in this test. How many cells you need to fill in, or how many cells you need to calculate using the probability approach before you can subtract to get the rest. And in a 2x2 table, it's only one of them. So there it is. If you go ahead and do these subtractions, what you get for the other four cells. So under the assumption of independence, as you'd expected, the number of death penalties would be about the same for whites and blacks. It's a little bit more for blacks only because there are more of the total. And for each of them, the number of non-death penalties is much greater because that's what it is overall. Which brings us to the Pearson chi-squared statistic. This is a pretty simple statistic to calculate. All you have to do is for each cell in that table, you take your observed number of counts, subtract what was expected, you square that and divide by the number expected, and add that over all the cells of the table. So it's something you could do with a calculator. This this Yates correction makes the chi-squared statistic a little bit more accurate for a 2x2 table. And if you're going to do it manually, you would add this correction to the chi-squared statistic. If you use SPSS or other software, the correction to it to make this fit the theoretical chi-square distribution will be done automatically for any size of table. But it's kind of just a curiosity for the 2x2 table when you're doing it by hand. But this is important, how to calculate the chi-square statistic, because under the null hypothesis of independence, it follows a known theoretical distribution. This chi-square distribution with r minus 1 so the number of rows minus 1 times the number of columns minus 1 degrees of freedom. So in the 2x2 table, it's the chi-squared statistic with 1 degree of freedom. Like the t distribution, there's a different distribution for every number of degrees of freedom. And this is, of course, because even if the null hypothesis is true and there's no association between those two variables, we're still going to have sampling variability. Even if your probability of receiving a death penalty verdict is independent of race, there will be some differences in any sample just because it's a probabilistic event under our analysis, and I think in life as well. It's not a completely deterministic event. So you're very unlikely to actually see your exactly expected numbers in each cell of the table, right? Here's what your chi-square table in the back of the book looks like. And what it's giving you is an upper tail area. This distribution is different from the z and the t distributions in that it's asymmetric. It's kind of, it goes down to exactly 0. It's never negative, right? Because we're squaring the numerator there. There's no way it can get a negative value. And it's extremely skewed to the right. So in this table, it's giving you the area under the right-hand side of this curve. And so you can look up for any alpha from 0.995 to 0.005, 0.05 being the one that you usually want to look up for the number of degrees of freedom to see what the critical value of chi-squared is for your test. So for the example that we just did, if we're using an alpha of 0.05, we have 1 degree of freedom. The critical value of the chi-squared statistic is going to be 3.841. Can anyone tell me how we're going to use that in our hypothesis test? Yep. Exactly. We compare that value to the value that we calculate from the previous formula. Yep. So if the value of chi-squared that we calculate exceeds this critical value, then we're going to reject the null hypothesis, because that means that if the null hypothesis is true, there's only a 5% chance that that we would see that much departure from independence in our table. It means that in this chi-square distribution, in our table, the departure from independence lies in this right-hand tail of the chi-square distribution. Just a few remarks. If the rows and the columns are independent, then our observed and expected values are not too different, and we get a fairly small value of chi-squared. If they're very different, then you get a large chi-square value, and if it's large enough, as we just said, then we'll reject the null hypothesis of independence. And this is different from the tests you've done already in that the alternative hypothesis is inherently two-sided in that it doesn't matter which proportion is higher than the other, either way leads to a larger chi-square statistic. But we don't do any doubling of the right tail area with chi-squared, because any way that you depart from independence sends you into that right-hand tail of the chi-square distribution. Here are our assumptions. As always, we assume that each observation is independent, and we assume that the sample that we're observing is representative of the population on which we're making the inference. We're also making an assumption of large sample size here, and a rule of thumb that you can use is that no cell in the table should have an expected number of counts less than 1, and no more than 1/5 of the cells should have an expected number of counts less than 5. So we're well into that large sample region in this example. For small samples, you could use the exact binomial test that we've covered already in class using the binomial distribution. There are also options, I don't think SPS offers it, but to do a permutation test for the chi-square to actually get an empirical estimate of that chi-square distribution rather than using the theoretical one. As an aside here, it's a pretty common practice, and I think I mentioned this at the end of class again, but to use a Fisher's exact test for these small sample cases, I don't recommend that because the two tests have different null hypotheses, and I think if you're considering using the Fisher's exact test, you need to, and I don't even cover it in this class because I think it's fairly rare that it's applicable to public health data analysis. But you need to ask yourself whether that null hypothesis is applicable to your situation, and then decide based on that whether to use Fisher's exact test. If there's time, I'll talk a little bit more about that at the end of class. But there is no assumptions on the population distribution here. We're just talking about proportions. So the only differences in distribution that we have are in the proportions in the table. We're only making the assumption of large enough sample size. All right, so what do we get if we do this analysis in SPSS? From the actual data from this paper, fortunately it's only a 2x2 table, so it's not difficult to go and put the data into SPSS. The observed counts here, 236, 128. Compared to the expected counts, And we get a chi-squared statistic of 39, which far exceeds that critical value of about 7, I think it was, and has a p-value of something very, very small. So we're going to reject the null hypothesis of independence. And then obviously we're going to want to ask, where is that departure coming from? What is the dependence that we see in the data set? So where is it coming from? And actually, I'll go back to here, looking at the proportion receiving the death penalty among whites. It's about 236 out of 4,600, and for blacks, 128 out of 5,000. So it's actually about twice as high for the white defendants, which is kind of interesting. The proportion of death penalty verdicts among white defendants is 4.8%, and it's only 2.5% among the black defendants. There is more to it, and I'll get back to that later after I introduce risk ratios and odds ratios. So your risk is just the probability of a given outcome. In this case, a risk of receiving the death penalty if you've been convicted of murder. And so it's just, in this case, it would be, so the probability of death penalty, and we're interested in it conditional on race here. So we have a risk for white defendants would be the probability of death penalty given that the race of the defendant is white. And the ratio is just the ratio of that conditional risk for white defendants divided by black defendants. Just arbitrarily putting the white defendants on the numerator here, so we'll get a number greater than 1, and it's 1.94, meaning that the risk of receiving a death penalty verdict for white defendants in this study is almost twice as high as for black defendants. So that's risk. Risk is simple. Odds is a little bit less intuitive unless, I don't know, you're used to gambling, I guess, where odds are used. Instead of that just being the probability of the event, like risk, it's probability over 1 minus the probability. So it's like the probability that your event happens divided by the probability that it doesn't happen. So it's a ratio. And it's a little bit more complicated to calculate, just there are more numbers in it. But you'll see here that it comes out pretty close to the same, 1.94 for the risk ratio and 1.98 for the odds ratio. An important distinction between odds ratio and risk ratio is that there are 2 different ways that you can calculate an odds ratio. To bring in another scenario, and rather than death penalty and race, the one more common to in public health, disease and exposure, you could calculate your odds ratio using the probability of disease given the exposure and divided by your probability of disease given that you're unexposed. So this is just equivalent to the last page where the disease is death and the exposure is race. But you can also switch it around and calculate it the other way, using the probability that you're exposed given that you have the disease, and the probability of exposed given that you do not have the disease. Whereas with risk ratio, there's only one way to do it. It's the probability of disease given you're exposed divided by the probability of disease given you're unexposed. Can anyone hazard a guess as to why this is important? Yes? Study design. Yeah, so it has everything to do with study design, and you're right. For certain study designs, this probability of having the disease given that you're exposed is something you can calculate from your data. And in particular, this is something that you can calculate if you have a representative sample, where your probability of disease is representative of the population. But if we have something like a case control design, where we've picked out a certain number of cases and a certain number of controls, then that probability, it doesn't tell you anything about that probability of disease given that you were exposed or not exposed. What it does tell you about is the probability of exposure given that you have the disease, because you've picked out people because they had the disease or not. So you can use this OR2 calculation in a case control study. You cannot use the OR1 calculation, and you cannot use the risk ratio calculation in a case control study. There it is written out for you. The only way you can calculate the risk ratio in a case control study is if you know what the prevalence of the disease is in the population. And then you can use Bayes' rule, as you've learned how to do, to invert that conditional probability and calculate the probability of disease given exposure and probability of disease given non-exposure, using your Bayes' rule calculator. Any questions? So as we noticed before, the odds ratio and the risk ratio were pretty close to the same in this example, and that is because the risk of death penalty was fairly low. It was only something like 5% or 2%, and overall somewhere around 3%. So for rare events, risk ratios and odds ratios are about the same. You know, if the risk of something happening is 1 in a million, then 1 in a million is your risk, and 1 over 999,999 is your odds, and they're almost the same thing. But for more common events, they can be quite different. So with the dice roll, your risk of getting a 1 is 1/6, and your odds of getting a 1 are 1 to 5. Because there's one way you get a 1 and 5 ways that you don't. We use odds ratio a lot in statistics, largely because it's convenient. And when you get into logistic regression, there is an easy transformation between probability and odds that you can always do. It doesn't matter. The population proportion doesn't matter. So it's something that you can always use, and it's what the methods have been developed around. But if you remember your Bayes rule and you know the prevalence that you're applying it to, you can always convert it to a risk and a risk ratio, or even a risk difference. So back to this example. It turns out that there is more to the story if you stratify the data set by the victim's race. So here we're looking at the same tables of observed and expected counts, but for the white victims only. And here we see an odds ratio for white defendants divided by the odds for black defendants of 0.36. So if the victim is white, then the black defendant is much more likely to receive the death penalty. And if the victim is black, it's the other way around. The white defendant is more likely to receive the death penalty, although this is an extremely rare event here. The paper itself summarized all of this really nicely in one table. This is an excellent example of a simple descriptive statistics table that really gets a point across with a minimum of stuff for you to look at. And I'm gonna maybe try to make this a little bit bigger. So among all cases, there's a 3.6% probability of receiving the death penalty. It's 4.8% for white suspects and 2.5% for blacks. But if you look at it instead overall by white victims and black victims, with white victims, your probability of receiving the death penalty is 6% compared to 1% for a black victim. And then if you look at the frequency of the crimes by black kills white, white kills white, you see that the well, first you see that the most common crimes are white kills white and black kills black. That's the majority of all of the murders. But it's in these cases. So, and if you look at those two, white kills white, it's a 5% probability of death penalty. But for when it's a black kills white, it's a 12.6%. So, so this is, I guess, an example of an interaction, in that it seems to the results look different depending on how you stratify this analysis by race of the victim. For the black victims, probability of a black receiving death penalty is the lowest of any of them. And then it's sort of moderate again for white kills black. So it's a pretty interesting paper. And there have been more recent analyses of these, and the data sets that I was thinking of that would be very interesting to analyze are some of these traffic stop data sets that have made it into the newspapers recently, and about outcomes of traffic stop depending on race of the driver and of the police officer. So overall, the race of the victim is the stronger predictor, but there does seem to be an interaction between race of the defendant and race of the victim. And because this is an observational study, obviously we can't make conclusions about causality of it, like what the causes for this are. That becomes a sociological or other study. All we can say from the statistical analysis is that application of the death penalty in Florida over this 10-year period is not independent of race of the victim or the defendant or the particular combination of victim and defendant's race. And just finally to note, all of that analysis, that table that they provided of the proportions is what allowed us to understand where the departures existed and to start making conjectures or arguments about why that departure existed. All the chi-squared test did was tell us that these variables are not independent. And so you can go and start looking at the differences and be confident that those aren't just differences caused by sampling variation, that there's a systematic association between race and the death penalty in this data set. Okay, we're almost done here. A few related tests. The McNemar's test you can use for paired samples, and the exact binomial test for small samples. And as I noted, this Fisher's exact test, which really does get frequently used for small samples, but it's for a different hypothesis. So for Pearson's chi-square statistic, we calculate the margins of the table. There's no need for them to be fixed by the study design. For Fisher's exact test, the case that Ronald Fisher used to explain or motivate the test was this lady tasting tea, where an English lady is given 10 cups of tea, 5 where the milk was added before the tea, and 5 where the milk was added after the tea. She's given them and told that there's 5 of each, and told to identify which had the milk added before the tea. Now, if she correctly identifies all 10 of them, what is the probability of that under H0, the null hypothesis, where she's simply guessing? The key thing about the design here is that the lady is told that first the total number of cups of tea was fixed by the study design, and the lady was told that there are 5 and 5. So she's going to make a guess that 5 of them have the milk added first and 5 of them have the tea added first. So all of the margins of that 2x2 table are fixed in the design of the study. And that is what the null hypothesis for Fisher's exact test requires. The lady is not going to guess 8 and 2 because she knows it's 5 and 5. If we didn't tell her that it was 5 and 5, obviously her odds of, under the null hypothesis that she's just guessing, the odds of her getting the correct guess are going to be smaller because there are a lot more guesses that she could make. So, I've heard someone said, I thought kind of saliently, that Fisher's exact test gives you an exact p-value to a different question. You just need to think about what is the question that you're trying to answer with your hypothesis test. What is the null hypothesis? Any questions about this Fisher's exact test? It's a pretty, I think that the lady tasting tea is a great way to remember what the scenario is when you can use Fisher's exact test, and how it differs from the, in the example we did with race and the death penalty. None of those margins are fixed in advance. So it would not be appropriate to use
Fisher's exact test. So you can use today's methods anytime you need to do a hypothesis test with two categorical variables. We use them today for binary variables, but they can have more than two levels. The null hypothesis is that those two variables are independent. Doesn't matter whether it's a binary and a 3-category variable or a 3-category and a 4-category variable. It's the same approach, and the null hypothesis is independence between those two variables. The tests are two-sided or multi-sided in that it doesn't matter in which direction the departure occurs. Any kind of departure will cause an increase in your chi-square statistic. So you only use the right-hand tail of the chi-square distribution. And as with before, the type 1 error is when you reject the null hypothesis of independence when the null hypothesis was true, and the type 2 error is when you fail to reject the null hypothesis even though it's false. So that's all we have for today. Actually, one other announcement that I'll make. I did post a makeup exam on Blackboard. If you want to take it, the rules are you do it at home. It's more like an assignment, but in the end, I will split the difference between your original exam score and the best of 2 attempts at the makeup exam. So if you got 70 on your first one and you get 100% on the makeup exam, then you'll get an 85 for exam number 2. I'm allowed you to use 4 hours, but it's about the same length or a little shorter than the original exam, so you shouldn't need 4 hours to do it. And unless there are any other questions, the deadline for the makeup exam is December 20th. Then we'll get on down to lab.